Hi folks, so this is question 10, and so we're getting into some probability here then. So an athletics competition, there were a number of heats in the 1500 meter race. So in the heats, the times that it took the runners to complete it were approximately normally distributed. So the mean was, so if we look at the normal distribution, the mean was 225 seconds. So we know that mu is 225 and the standard deviation is 12. So we want to know, that's the mean in the middle there, we want to know the percentage of runners who took more than 240 seconds. So 240 is going to be out here then. So we're going to be using a z-score. So a z-score is x minus mu over standard deviation, so you can work all that out. So it's going to be 240 take 225 1 over 12. And we get 1.25. So if you think about it, so 0 is here, our z-score is here, so z is 1.25. So we're interested in the percentage who took more than that then, so we're interested in this percentage here. So we want the probability that z is more than 1.25. So your tables won't let you find for greater than, so you have to, we're going to do 1 minus z is less than 1.25 because our tables only lets us read to the left for less than. Right, so if you go into your log tables then and look for a z-score, so you're going to go down the side and look for 1.2 and then where it meets 5, so 1 for 1.25, so that's what you're looking for in the z-score tables, and you should get 0.8944. So that's then how much is on the left hand side of that line, but remember we're interested in the red part there and in what's to the right of it, because we want to know what's greater than. So we do 1 take away 0.8944 and its final answer then is 0.1056. And they wanted us to give it as a percentage, so yeah, if you multiply by 100 it's 10.56. So that's the final answer. Right, so for the second part then, there's the 20% of runners with the fastest times. Okay, so we have to work out the time needed to qualify. So if you think about it, the people with the fastest times would be the ones who have the lowest times. Remember, so the lowest time in a race is obviously the best. So the lowest kind of 20% would be in there. Okay, so that's the lowest 20%. So this is kind of what we want. So, and we want the kind of the time down at the bottom. So remember in the Z tables then you can't kind of go that way. So if we flip it around, and put our 20% in here, so it's the Z score that's down here then. So remember our mean is 225, so it's the Z score that's at this point here. That's really what we're looking for. So we're using the fact there has to be 80% here then, and there has to be 20% in there. Okay, because that's the because it's the fastest 20% we're looking for. So we're looking for the Z score then, basically that's closest to 80%. So we're looking in our tables, and you're looking in the middle of the tables for one that's the closest to 80% and what score that would be. Now, so if you look in your log tables for the closest one that would be 80%, so you can see it here, it's going to be the 0.7995. So you can see 0.6, so this is on page 36 of your log table, so it's 0.7995 there, you'll see it in kind of in the middle towards the bottom. If you look for if you kind of go to the left then and look out at the column on the left, it's 0.8, and then if you go up it's 0.04, so 0.84 is what we're getting. So 0.84, that's the closest one to 0.8 or to 80%. That's in the log tables. So our Z score then will be, if you flip it back around again, because really we're looking down here at what the fastest 20% were. So that will be minus 0.84 then. Would be the Z score there. Would be the Z score in there. So minus 0.84 is what we're dealing with. So we're going back to the formula from the first part then. So the Z score is equal to x minus mu over standard deviation. So really what we want is the x. So the x will be the actual time that people needed to get below then. And we know everything else now, so minus 0.84 is the Z score, equals x minus mu is just 225, all over standard deviation of 12. So what you have to do is you just have to bring across the 12, multiply it by minus 0.84, and once you've done that then you bring across the minus 225 and you add it on to whatever you got on the left hand side. So x is going to be equal to 214.92 seconds, and that's the final answer for that part of part A. Right, so for part B then, we have to work out the probability that she makes her first false start in her 4th race. So let's look at the first 3 races first. So the probability that she makes a false start in any given race is 5%. So for the first 3 races, we need the probability that she doesn't make a false start in the first 3 races, because she can't make one in the first 3 races for what we want. We wanted it to happen in the 4th one exactly. So it's going to be a Bernoulli trial. So it'll be 3 choose 0. So this is the probability that she doesn't make a false start in the first 3 races. So 3 choose 0 times by 0.05 to the power of 0 times 0.95 to the power of 3. So because 0.05 is the probability that she makes a false start, and 0.95 will be the probability then that she doesn't. So that would be the probability for the first 3 races she doesn't make one, and then we need to just put in the probability then that she does make one for the 4th race, and that will just simply be 0.05. So we just times it by 0.05. And you can put all that in together into the calculator and it'll give you your answer. So 0.0429. And that's all for part B. Right, so for part C we have to find the probability that that at most 2 teams. So if it's at most 2 teams drop it, then no teams could drop it. One team could drop it, or 2 teams. So no teams, 1 team, or 2 teams. So if it was 3 teams that dropped it, it wouldn't fit into what we want here. It wouldn't be within that probability. So we just need to calculate it for each of them and add them together. So for no teams, it's going to be, now there's 20 teams in it, so it'll be 20 choose 0. So this is for no teams, and then the probability that they drop it is 0.1. So it'll be to the power of 0, and then the probability that they don't drop it has to be 0.9. And that's to the power of 20 then. So we're going to add that on to, that's the probability that no teams drop it. Then we're going to add it on to the probability that 1 team drop it. So that's going to be 20 choose 1. And again, it's 0.1, and it will be to the power of 1 this time, times 0.9 to the power of 19. And then we're going to add on to the next, to 2 teams dropping it. So that's, again, it's going to be 20 choose 2. And 0.1 to the power of 2, 0.9 to the power of 18. And when you put all, you can put all that in the calculator together, and you could work each one out separately and add them if you want, but you could just, if you're careful, just put everything in, and you should get 0.12. So that's the probability. Sorry, actually, it's the 4 decimal places, isn't it? So 0.1, 2, 1, and 6, I think, when you round it off to 4 decimal places. Right, so for part D then, so we have to work out the probability that the sum of their numbers is 101. So that the sum of their numbers is 101. So there's 300 in the race. Each runner has a number from 1 to 300. Right, so if you think about what numbers would add up to 101, you could have 1 and 100. So that person, or those 2 runners, that kind of fits the bill there, that they add up to 101. So the runner with 1 and the runner with 100. And then another one would be 2 and 99 because they add up to 101. Another one would be 3 and 98. And 4 and 97. So we could keep going on. But you should get the picture. And then the last one kind of in the list, if we keep going that way, would be 101. So there's 100, if you think about it, there has to be 100 of these people then. So there's 100 people who it could work for. So 100, or 100 ways that 2 people could add up to 101. Now, if we focus on the kind of the individual probabilities of this happening, so if you just look at the probability of that happening, that the one person is 1 and the second person is 100, if you pick them at random, so the probability that you pick somebody, so just look at the first person, the probability that you just pick someone in a race and that they have the number 1, well, that has to be 1 out of 300, because there's 1 in 300 chance that you pick the person that has 1. And then you must multiply that by the probability that another person that you pick has 100 on their back. So you've already taken one person, you already picked one person, so that's going to be 299. So this here then, this would be the probability that you pick 2 people at random and that the first person has the 1 and the second person has 100. But that's only for that outcome then. So what you have to do then is you have to add on the probability of this happening, that you pick somebody at random and they have the number 2, and then you pick another person at random and they have the number 99. So again, it's going to be the same probability. It'll be 1 over 300 times 1 over 299, and so on, and then you have to do it for the next one and the next one and the next one. So remember we said there's 100 different ones of those, so we're just going to be multiplying that 100 times, so the probability never changes. It's 1 over 300 times to 1 over 299. So we're just going to do that times by 100. So all we're going to do to work out the answer is 1 over 300 times by 1 over 299. All of that times by 100, because there's 100 different ways. And you should get 1 over 897 when you calculate that. Right, so for part E then, I think it's the last part. So we have to find out her position in the Sunny Marathon. So we know her finishing time for both marathons was the same. So if you put it on the normal distribution again, we know that the mean was 254. So that's in the middle here. So if you think about it, if she finished here 5265 position, well then if you think of all the people that would have came before her, so we want to know kind of how many people came before her out here. So that would be 5264 out of 6,000 altogether, so out of 6,000 athletes, and then if we times that by 100, it gives us the percentage of people who finished before her. So 87.73. Percent. So if you look at it on the standardized Z tables, then so what we need really is this Z value down here. So we know that there's these are the people who finished, so 0 is here, so these are what we've shaded in here is the people who finished before her, so that's 0.8773. Just changing it to a decimal. So we're going to go back to our log tables again and look for the Z value that's closest to 0.8773. So this is just taken from the Z tables then. So we're looking for the one that's closest to 0.8773. So we, you might be able to see here then, you've got a 0.8770 here, and I think that's the closest one then. So this one here is 8790, so that's further away, and then this one here, that's further away as well. So we're going to take this one here that I circled, so it's going to be 1.16, because we're putting those two together, so 1.16. Okay. So we can work out her actual time then for the Windy Marathon by using kind of the same trick we used in one of the questions before. So x minus mu over standard deviation has to be, that's the Z score then, so that we know that 1.16 is the Z score there on the normal distribution. So we want to know what x is, that will be the time, so we take away the mu, so mu is 254, and the standard deviation is 38. That has to be equal to 1.16. So then you just need to move the 38 across the equal sign, multiply it, and then add on the 254, and you get what x is. So we get 298.08. So that is the x value then. That's the time in, it must be in minutes, I'd say. Yeah, time in minutes in the table there, sorry. So minutes. Right, so for the other marathon then, for the Sunny marathon, let's just put in the information we know. So her finishing time is the same, that's why we needed the other thing. So the x for this one then will be the same as, so 298, so this is what we worked out, 0.08. The mu then for the Sunny marathon will be 247. And the standard deviation is 29. So we can work out a z-score for that then. So z is equal to x minus mu over standard deviation. So 298.08 minus 247 over 29, and we get 1.761. So that's our z value then. And really we want to know how many people finished before her again. So if you look that up in the tables, then you get 0.9608. So if you look up as what the z-score of one, or the proportion of what would be less than that z-score, it's 0.16 or 0.9608 in the log tables. Now that's the same thing as 96.08%. So we want to know how many runners finished below her then, and there's 2,000 runners altogether in the race, so there's 2,000 runners in the Sunny marathon. So we're going to find out that percentage of 2,000. And that is 1921. So 1921 runners. So those are all the ones who finished below her or finished quicker than her then. So if all those finished in front of her, then she had to be 1922 place. So 1922 will go back into the table up here. So a tough enough question, the last one, last part. But that's it, that's all for that question, and that's it for the whole paper.